Good day, this is Dr. T and a little bit of a different video. So I'd like to talk a bit about our different understandings of the atom, how that has changed over time. And I'm using a software developed by PHET, which is a nonprofit organization with University of Colorado Boulder. So this is, as you can see, models of the hydrogen atom. It's one of them. They haven't moved over to HTML5 yet. It's still Java, unfortunately. But hopefully in the near future, they'll be shuffling that over. So we've been talking about atoms, and one of the earliest models for the atom, or once again, a model is the idea of how we understand something. One of the earliest ones has been the billiard ball. And the billiard ball is like, hey, atoms are hard spheres. And this is actually the model we use the most. Hint, it's the least accurate. But for many applications, this is good enough. But the reason we know this is the least accurate is the way that atoms interact with light. So in this case, I've got the simulator. I'll get my light gun, or whatever the thing is, and I will shoot it at my hydrogen. And if it was a billiard ball, then photons would bounce off. And it wouldn't matter what kind of photon you'd have, they'd just all bounce off. But that's not what happens. When you have actual light, only certain photons are going to interact. Most of them will just go straight through it. And they don't really bounce off, they get re-emitted. So you absorb and re-emit. So this is just not working out. Not to mention, beginning of the 20th century, we start getting this idea that there's more going on. So the next model we have that comes out, it's called the plum pudding model. Think like bread pudding. So the idea is the electron is like a raisin inside the positively charged goo of the atom. Like you would have raisins in bread pudding or plum pudding. Problem with this one, though, is when you actually look at the mass of the atom is all concentrated in the middle. So this just doesn't make a lot of sense. Not to mention, it kind of doesn't give you the best predictions. It gives you some decent predictions, but what you see down here is your spectrometer, and your spectrometer is telling you the photons of light that it's absorbing. And that's not the spectrum of hydrogen. It's not lining up. So we got a couple other models. So we can imagine, hey, if all the matter's in the middle, then maybe atoms are like solar systems. You know, our solar system, almost all the matter's in the sun, a nice block in Jupiter, and everything else is not much. Yeah, that's not going to work. If atoms were solar systems, then, you know, the electrons, if they were like planets, would either fly off or spiral in at some point, and, you know, no atoms. So, yeah, that's not going to work. Next comes up, and all this talk of astronomy actually makes sense because this guy, Niels Bohr, is an astronomer. He's trying to understand hydrogen specifically. And he comes up with the Bohr model. And there's actually a little bit of debate in the educational circles whether or not I should even be showing you this. Because the Bohr model is a gross oversimplification, but of course the billiard ball model is a whole lot more simplified. So this is really our first model that starts making some predictions that make sense. If you looked at the spectra you're getting out for hydrogen, yeah, it's actually looking pretty good. We're actually seeing what you would get emitted from hydrogen if you send light into it. So this is starting to work. The problem with the Bohr model is that, well, it works actually pretty good with hydrogen. And I should caveat, this is working well with an hydrogen atom, or I guess it would be a hydrogen atom, all by itself in a vacuum, not touching anything. There's a lot of assumptions here, and they all tend to actually work out reasonably well for the outer layers of the sun. They don't like work anyplace else. Some kinds of discharge lamps that works decently. So there will be a bit of hand waving and a lot of assumptions that we're making just to simplify things out because nature gets real complicated real fast. But anyways, we're getting a spectrum that actually works. For hydrogen, it works fine. For helium, it actually works good enough that that's how we discovered helium, is understanding the nature of the Bohr model allowed us to realize that we had something that had 2 electrons and 2 protons in it. And boom, you've got helium. That was actually discovered on the sun. It was later discovered on Earth. So we've got ourselves a model of the atom. Now, in this model, let me give you a brief rundown of what's going on here. So we've got the electron. It's orbiting around in what we call orbitals. Now, this is going to change once we get down into Schrodinger's model, because we're still assuming the electron's a particle at this point. And that's going to change here on the next model. But the electron's buzzing around, and once again, buzzing is probably the best word here. It's going around the nucleus, and so kind of like that planetary model, but it's locked in these very specific shells, is what we're going to end up calling them. So it's going around these shells, and we're going to call them, the closest to the nucleus, or in this case, the red dot. We're going to call that shell 1, the next one shell 2. Now, there's no intermediate. The electron cannot exist in between two shells. So there's no existing at shell 1.5. Now, when a photon comes in, and you should be able to see it happening there, the energy from the photon is used to kick the electron from shell number 1, or what we call the ground state. Basically, all of the electrons packed in as tightly as possible. Now, you only got one, so as tightly as possible is right at the bottom, or in the middle. We're going to use energy to kick that up to a higher shell, what we call an excited state. Now, once we're up at that excited state, then, well, it's going to fall down, and it's going to give off energy. Now, it may fall all the way straight back down to ground state, or as you notice, it's occasionally jumping off and kind of hopping, making a couple of hops. Each hop is going to take energy away, and that energy comes off as a photon. And as you notice, once again, different color photons are coming off. The black ones are supposed to be ultraviolet. There was a red one, a little bit lower energy, as they're traveling through. Okay, so we got our model, but this has a couple of fundamental problems. One, it only really works for hydrogen. It works okay for helium, but not great. The math is simple, fairly straightforward math. But once again, if you're over anything other than hydrogen and helium, the math doesn't give you the good data. It gives you data that you expect, one peak, and you actually get 3 peaks and other things. Not to mention, the other question is, what is going on? Why can there not be a shell 1.5? What is going on with this? Why are these shells things? Well, the first question is going to take a little bit more to go with, but let's go with the second part of that, and why are these shells things? So this is the Bohr model, and so in this case, what we're looking at is we're changing our idea of what an electron is. So the Bohr is a little bit later than Einstein. And what he has realized from Einstein's work on photons is that photons are wave particles. They're both have this duality, this dual nature, both wave and particle. And de Bogle asks kind of the reasonable question, well, if a photon's a wave particle, maybe something else is too. It's one of those, once you find one elephant in the refrigerator, you gotta wonder if there's two, Obviously, I'm being slightly sarcastic there. So de Bogle runs the math and realizes that this duality is going to be biased towards the mass. So a photon has no mass, so it's actually more wave-like in many respects than it is particle-like, although really it's got that true duality. And once you get up something as massive as, say, a proton, then the wave nature of it is basically ignorable. But an electron's a lot smaller than a proton. Electron's small enough that it's actually still pretty wave nature-y. It's still got a lot of that wave nature going on in it. So what if we stop assuming that the electron is a particle buzzing around? We already know kind of from Heisenberg that you can't pin these things down. What if the reason you can't pin them down and get their exact velocity and location is the fact that they're a wave? And asking, where is this wave at, to the millimeter kind of thing, if it's an ocean wave, it's kind of silly because it's big. Where is the wave at? Well, it's all over the place. This actually makes a lot of sense here with those shells, because if you've got shells have to be an area where you can have a standing wave. Because if it wasn't a standing wave, then the electron would cancel itself out, it would cease to exist. Now, these are kind of more of a probability thing, so we're going to also go with this idea of electron is most likely in this location. With waves, they can be in other locations as well and do other crazy things, but we're going to kind of ignore that fact. Now, a standing wave is this wave where, as the wave travels through whatever it's traveling through, and of course, kind of electron and photons don't really travel through anything, that it's going to have certain regions that are called nodes, and these nodes don't move. And the goal of the standing wave is that the nodes are going to line up, because it's probably bounded on two ends, or in the case of the electron, the shape of where it's waving requires it to be effectively bound. So this means your nodes have to stay in the same spot. They have to not migrate around. So your frequency has to be such that if you were to travel around your circle or travel down the line and bounce off, that when you are going back over places, that your nodes the first time and the second time and every succinct time would all line up. Otherwise, you would start canceling yourself out. And this is actually how a stringed instrument works. Actually, this is how basically all instruments work, but stringed ones are the easiest to say. So if you're, say, a violin player like myself, I'm not a particularly good one, but I have played the thing, you know that the way you control the frequency of your strings, which controls the note that you're playing, is you pinch down on the string. Only certain frequencies will have the right wavelength for that particular string to go from the bridge to your finger, bounce back, and have the vibrating parts of the string being in one spot and the nodes being in a different spot, and they stay locked in those locations. And thus you can fix which note you're playing, which of course is the frequency, and then all of the other higher frequencies that can add into it, what we call harmonics. But that's enough about instruments. The idea here is that the electron has a frequency, and so the electron is almost like a note being played on an atom, even though, once again, metaphors aren't perfect. And so there's only certain regions around the nucleus that allow you to get the proper, electron note being played. Yeah, we've explained why on Earth these shells are things, but we haven't really improved our calculations that much. We still need to get these spectra lined up a bit better, especially cases where you don't get one line or one frequency of photons coming out or being absorbed, but instead you get through two or three. Now, when I'm saying lines, the reason we call them lines is that when you do measure this for a spectrum, in the old days you'd use a prism. Today you can use a prism. Usually they use what's known as a diffraction gradient, which uses thin lines and creates an interference pattern. But either way, you're going to be separating out your light based on frequency / wavelength. And when you're doing that, if you start out with, say, a slit, it's going to create the image of a slit, which looks like a line. If you're creating a bright line spectrum, that's where you have light coming in only very specific frequencies, so you have bright lines being created. However, if you have a, effectively a white light, but it's lost some of the frequencies, then it's going to be, light everywhere except for where you get those frequencies that are being absorbed, and we call that a dark line spectrum. As chemists, we typically use bright line spectrum. Astronomers, because the black body radiation gives you white light from, say, a star, they're looking at the dark line spectrum. They're the same spectrum, the lines occur in the same spot, because you're always dealing with energy transitions, and the transitions are the same whether the energy is coming out or going in. But we got to line these things up. They're still not quite ordered. Okay, so this is where Schrodinger comes in. Schrodinger comes up with the ideas like, okay, de Vogel and Bohr, they've got the electron going around basically in circles or spheres, as the case may be. What if the electron is not? What if it is going in a more intricate pattern? So maybe the math needs to be somewhat more complicated, and jumping into the actual math for Schrodinger is well more than I care to get into. I took that class, I passed that class somehow. So looking at what we've got, Schrodinger comes up with the core idea of saying, what if instead of one value, this shell value, it's actually more complicated. So Schrodinger comes up with four numbers. Now, only the first three are being shown here. These are called quantum numbers. So the first quantum number is the principal quantum number. That's the in the equation. And that's basically exactly the same as Bohr's shell. So yeah, so everything you just learned on the Bohr system basically is still applying to that shell. And that's going to give a number that's between 1 to however many you want, but it's going to be a whole number. So it has to be, 1, 2, 3, 4, 5, 6, whatever. Okay, now what Schrodinger comes up with the idea is like what maybe shape. So then we get the other three quantum numbers. So the next one's going to be L. L is describing what shape the electron is doing. Because remember, it's a wave, but a wave that's going around or existing in could be a sphere, could be a donut shape, some kind of, three-dimensional figure eight. And this is called the angular momentum quantum number. And this is going to be from 0 to whatever your n is. And once again, in whole numbers. So if n is 2, it is going to be either 0 or 1. And I just said it was 0 to n. It's actually n minus 1. So my bad. So it's going to go from 0 to 1 less than whatever your n is. So if my n is 2, I can either have an angular momentum number of 0 or 1. Now, these momentum numbers actually got some interesting names. So it was originally thought by spectroscopists, people who do spectral work, that there were different types of lines, and they still talk about these different types of lines. Some that they were called sharp lines, some that were called diffuse lines, some were called fundamental and principal lines. So thought that sharp lines corresponded to L equals 0, principal lines corresponded to L equals 1. They don't. This was one of those really cool hypotheses that's really kind of a shame that's not true, but it's not. That said, the idea stuck of calling each one of these angular momentum numbers by a letter occurred. So the idea is that what we're dealing with are known as orbitals, and that they come in different shapes. Now, these are not orbits. They're completely different from orbits. We already saw what happens when you have an orbit. These are orbitals. And that S is going to be, L equals 0. It's a sphere. And so this is kind of a region in space. It's spherical in nature, that the electron will more than likely be in that region. Something. Because remember, the electron is a wave, so it's not like it's moving around. It's an electron. Then L equals 1, that's going to be a P. P's are kind of dumbbell shaped. L equals 2 is going to be a D. That's going to be kind of cloverleaf shape, except for one of them, because the higher the L number, you get more possible orbitals or more orbitals of that type. So D's can also be kind of a dumbbell with a donut on it. And then F is going to basically look like a D, but doubled. So a double clover leaf or a dumbbell with a double donut kind of scenario. And there's G's and H's and whatnot, but you don't usually have to deal with this. Now, the next quantum number, M, is usually written M sub L. And that's going to be our magnetic quantum number. And as I was kind of alluding to previously, when you've got these orbitals, the regions that the electrons can buzz around in, for S, you only get the one sphere. But if you have a donut, or sorry, not a donut, a dumbbell, I don't know why I keep thinking donuts, but if you got a dumbbell, you can put it in multiple orientations. So if you put an XYZ graph over your nucleus, then you could imagine a dumbbell going on the Z, which we would call P sub Z. and a dumbbell pointing around the x, which we call p sub x, and the y, p sub y. For the p's, so magnetic quantum number, or sorry, angular quantum number 1, then you get 3 possible choices for which orientation you have. So you get 3 different p orbitals, and it's not like you get one of the 3, you get all 3. So you'll have electrons hanging out in any of these locations, or if it's what would become an excited state, these can be empty. These are just regions in space where the electron can be if it is properly energized for that. So it goes by a fairly standard add 2 pattern. So there's 1 s, there's 3 p's, 5 d's, I can't add, and 7 f's. Presumably, if you had an h, there would be 9 g's. Sorry, can't do algebra, or can't do letters either. Now, these are going to be associated with a number, and it's going to follow that 2, 3, 5, 7 pattern, obviously. So for L equals 0, M sub L can only equal 0. For L equals 1, then M sub L is going to be minus 1, 0, or 1. You're going to kind of see a pattern. It's going to be minus L, whole numbers, albeit negative ones, up to 0, and then whole numbers, now positive, up to whatever L is. And this, you basically are expanding in pairs. So for D, that's L equals 2, you'd have minus 2, minus 1, 0, 1, and 2. F, minus 3, minus 2, minus 1, 0, 1, 2, 3. Yay. The last one we have is going to be spin. And the spin of the electron is going to be an interesting feature. For lack of a better description, and this is one of those, it's kind of a fuzzy idea, because remember, they're a particle and a wave, and waves don't exactly spin. But imagine it's a particle, and it's like they're spinning on like a top. They can, spin clockwise or counterclockwise. So we give them a description of spin that's either minus 1/2 or plus 1/2. Because anything charged that's moving or spinning is going to create a magnetic field. This will create a magnetic field. So within any of these orbitals, you can have up to 2 electrons. One must spin one way, one must spin the other way. Doesn't matter which way they're spinning, but you've got to be opposites. If you only have 1 electron in your orbital, it can do whatever it wants. But if you have 2, they have to go opposite. So the 4th quantum number, which is not listed here, is usually M sub s or just s. M sub s is a better description. And that is either going to be plus 1/2 or minus 1/2. Now, when you've got electrons, one of the interesting things when you're looking at them is that you have to have unique quantum numbers. So if you've got a single atom, obviously if you got 2 different atoms, they're 2 different atoms, but the electrons in an atom cannot have the same quantum numbers, because that means they're trying to coexist at the exact same spot, and it's just not going to happen. So when you're looking at these, one of the things you do want to look at is make sure you don't have 2 of the same, because it's just not going to happen. Okay, so there's going to be more videos on this one as we go along. But with that said, have a wonderful day.